Now, my friends, one confusing thing about independence is this. In most cases, the students think that independence is a statement that they can assume. Independence of events actually is not something that we can decide. We cannot say that two events are independent from each other. However, the mathematical equation may state that. Okay? So if you want to prove that two events are independent from each other, you need to show that this equation holds. You need to show that the intersection probability is equal to the product of the individual probabilities. If you can show that this equation holds, then you can say the events are independent. You cannot just think that these two events are independent or not. You cannot make a decision on that by your perspective. Only mathematical equation must be tested, and by testing this mathematical equation, if you see that this equation holds, then you can say these two events are independent. And by the way, independence is a symmetric relationship. If E is independent of F, then F is also independent of E. So one of them is, if one of them is independent of the other one should be independent of the previous one as well. So it doesn't matter which event is supposed to occur first over the timeline. And another thing that can be proven mathematically, I'm not proving it, but stating it, if an event is independent of F, then that event is also independent of its complement. So we are going to understand this in this question. Suppose we toss two dice sequentially, and E is the event that the first die comes for. So I defined, again, remember, we are tossing two dice, and you know that the sample space of this experiment has 36 equally likely outcomes. And we define event E as the event that the first die comes as 4. And event F is the event that the sum of two dice is equal to 7. Okay? The question is asking this: are these events independent or not? So we need to check this. If E intersection F is equal to probability of E times probability of F, then these two events will be independent. Now check out. The event of E is what? The event of having the first die output as 4. And in our sample space, which contains 36 equally likely outcomes, this subset represents the event E, right? 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. This subset represents event E, and this subset has the probability of 6 over 36. So probability of E is 6 over 36. Now check probability of F. What is F? The event of having the sum of the upturned faces equal to 7. Okay? So in which subset of the sample space the sum of the upturned faces would be equal to 7? In this subset, right? 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. And in fact, because this subset has 6 elements as well, the probability of this event is also 6 over 36. And let's focus on E intersection F. What is E intersection F? The first die is going to be 4 and the sum is going to be 7. This intersection event can only be possible if the output is 4, 3. And the probability of having a 4, 3 as an output of this experiment is 1 over 36. And as you can see, the product of the individual probabilities is equal to the probability of the intersection event. And because of that reason, because this equation holds, we say that these two events are independent. Now coming to the next question. Now, suppose we toss two dice sequentially. Again the same experiment. We define event E as the event that the first die comes for. So event E is the same. However, event F is defined differently. Event F is the event that the sum of two dice is 6. So instead of having the sum of two dice as 7, this time event F is defined as the event of having the sum of the two dice as equal to 6. So this time I am asking the same question. Are these events independent? Now one can say, in the previous question they were independent. You have only changed the value from 7 to 6. Then this should be independent as well. This would be an unfortunate reasoning and is not a clever approach to solve this question. What is the clever approach then? The clever approach is the same. Again, you need to show if this equation holds or not. Now let's check the first event again. The first event is the event of having the first die as equal to 4, and this 6 element subset again corresponds to this event, and this subset has probability of 6 over 36. Now let's focus on event F. Event F this time is defined as the sum of the two upturned faces to be equal to 6, and this is only possible if the output is either a 1, 5, 2, 4, 3, 3, 4, 2, or 5, 1. So event F this time has a 5 element subset, and event F has the probability of 5 over 36. The sum of two dice is equal to 6 with 5 over 36 probability. And finally, the probability of E intersection F. Remember, E represents the first die to be equal to 4, and F represents the sum of the two outputs to be equal to 6. And this is only possible with one outcome, which is 4, 2. And this single outcome has probability of 1 over 36. Now, if you check this equation, the left-hand side, E intersection F, has the probability of 1 over 36. However, the right-hand side, my friends, has 5 over 216. If you multiply these two values, you get 5 over 216, and this equation does not hold, so they are not equal to each other. Therefore, these two events are not independent. So these two questions, question number 7 and number 8, are basically showing you are not the ones who are going to decide if the events are independent or not. Now we are going to use this information in a question. It says in a community, a family owns a TV with probability 0.8. So if you randomly choose a family, by 0.8 chance, this family owns a television, and a random family owns a car with probability 0.6. If you choose a random family again, they own a car with probability 0.6. Now, it says if owning a TV and owning a car are independent events, assume that owning a TV and owning a car are independent events. Then what is the probability that family owns none of these things? So what is the probability that the family, a random family, owns none of these things? So we are going to express again the given information in the question with set notation, and let T denote the event of the randomly selected family to own a TV, and the probability of T is 0.8, and C is the event of owning a car for a randomly selected family to own a car, and PC, the probability of event C, is 0.6, and we know that these two events are independent from each other, as it is stated by the question. Therefore, T intersection C, which is the event of owning both of these objects, the probability of this intersection event can be expressed as probability of T times probability of C. Why? Because the question states that these two events are independent. If the question does not state anything about the independence, you cannot use this equation to calculate the intersection probability. This equation can only be used if two events are independent. If it was a general equation, then we would have used this before. This equation can only be used if two events are independent. And in that case, the intersection probability would be 0.8 times 0.6, which is 0.38. Now the question is asking us, what is the probability that a randomly selected family owns none of these things? Actually, the question is asking the probability of this event. The family will own none of these things, which means T union C complement. So remember, T union C means the family owns at least one of these products, and the complement of this union is the event of the family to own none of these things. And let us find the probability of T union C in the first place, because the probability of the complement can easily be computed by subtracting the probability of the union. And the probability of union is what? The probability of the first event plus the probability of the second event, subtract the probability of the intersection event. all of 3 are available as an information in the question. We have calculated the intersection probability by using the independence assumption. And 0.8 plus 0.6 minus 0.48 is equal to 0.92. And this is the probability of the union event, the event of owning at least one of these things. And the probability of owning none of these things is 1 minus 0.92, which is 0.08. Now, moving further, a sequence of 5 independent trials is to be performed. Each trial results in a success with probability 0.4 and a failure with probability 0.6. What is the probability that no success occurs in 5 trials? The question states an important thing about these trials. So every time you perform a trial, they are independent. It says we are performing a sequence of 5 independent trials. They are independent. And at each trial, you either end up with success with 0.4 probability and failure with 0.6. If part A asks the probability that no success occurs in 5 trials, you should say each trial results with failure with 0.6 probability. So because of the independence, you can multiply the probabilities and get the ultimate probability of having failures in all of these trials. So having no success in any of the trials means having failures in all of the trials. Now coming back to part B. What is the probability that at least one success occurs in 5 trials? So in order to answer this question for part B, you can develop a simpler approach. If the probability of having no success is 0.07776, you can subtract this probability from 1 and end up with the probability of having at least one success. So because having at least one success is the complement of having no success in 5 trials. So part B can easily be answered from part A. Now part C. What is the probability that exactly one success occurs in 5 trials? Now, my friends, again, we assume independence between trials. Okay, in 5 trials, there's supposed to be a single success and 4 failures. And for that, we need to multiply the probability of a single success with the probability of 4 failures, which is 0.6 to the power 4 because of the independence between the trials. However, this probability that you see here is the probability of having the first trial as success and the remaining 4 trials as failure. So this is the probability of a single permutation of these success and failures. However, the question states that what is the probability of having exactly one success out of 5 trials? So this means what? Any permutation would work. So this success can happen to be in any of the trials. Okay? And in how many different ways one success can be occurring in 5 trials? In 5 different ways. Okay? So in the first case, the first can be success and the others failure. In the second permutation, the second can be success and the others can be failure. In the third can be success and the others can be failure. And there are how many different ways of doing this? 5 different ways. So therefore, we need to multiply the above probability here, 0.4 times 0.6 to the power 4, with 5, because that single success may happen to occur in any of the 5 trials. There are 5 possible different permutations to have these successes and the failures. Therefore, we need to multiply this probability with 5, so the probability of having exactly one success is 0.2592.